Hello everyone, my name is Ettore Randazzo and today I'm going to talk to you about recursively fertile self-replicating neural agents. So this work is about trying to find some self-replicating agents through differentiable optimization. And I'd like to start with giving a motivation as to why I think this is interesting or why it matters. So, to my knowledge, all biological species have some sort of self-replication, and the way they use it is very interesting to me. They use it as a diversity generating mechanism for surviving to an ever-changing selective pressure. And the offspring of each one of those agents is significantly different from their parents. It effectively is adaptable to most environments over many generations, so if you give them time to evolve. And it's also rarely cancerogenic. And while those things seem trivial, we do not have any human design system yet which has all of these properties. And one question that I have is, can we also use or learn from self-replication as a method for generating this kind of diverse and endlessly complexifying offspring? And alongside that, can we help construct a theory for generating complex systems through self-replication? I'll gloss over what I believe is the current situation about self-replication, and I'll start with the evolutionary strategies, which are the closest cousins to self-replication. However, they generally actually do not use self-replication. They just abstract away the concept of replication, and they make it fixed or close to fixed. And the largest limitation that I see in general with these approaches is that effectively they have a limited diversity of the offspring that they can generate. Sometimes it's because the encoding is very restricted. For example, it could only be limited to a specific kind of architecture or for accepting a specific type of inputs. But other times it's just because the system development does not reach arbitrary complexity. This is something that they have in common with the open-ended evolution field, where we still have yet to find an unbounded complexification of behaviors. And I hope that maybe the research on self-replicating systems could help with that. And I will try to show why I think that could be the case in a second. Meanwhile, with deep learning and differential optimization, the situation is even more scarce in the sense that there's very little work done in this area. The only ones that I found were actually done for this conference by Chang and Lipson and Gabor et al. And they use self-replicating feed-forward neural networks. However, there's still quite some work that needs to be done. In fact, as Gabor et al. Noticed, the agents were yet infertile and incapable of generating meaningful variation. I will explain what I mean by fertility later on. However, I believe that deep learning and differential optimization can help a lot for our task and endeavor, because they can help us with bootstrapping a species. So self-replication is likely going to be some routine which requires a lot of parameters. And this is where differentiable optimization shines, to find like the right configuration in a very high dimensional environment. And imagine this. We could, for example, train a model to be able to self-replicate while being able to solve a specific set of tasks and giving them the capability of variation, of generating offspring with variation. And after we do that, well, we can continue however we want. We could say, okay, we could continue with deep learning, but we could also just say, now let's use an evolutionary strategy or put these newly created agents into an open-ended world and we will have a bootstrapped species to begin with. And I believe that this would reduce the time complexity by several order of magnitude if our final goal is to generate complex life, because, well, we would start with some agents which can already self-replicate with variation, and that's probably, billions of years cut down of time requirements. So what we did in a nutshell, we advanced the field of self-replication through differentiable optimization by, first of all, highlighting the necessity for fertility in self-replicating agents. Again, I will explain what fertility is in a second. And we created a neural agent that encodes an image and is also capable of generating fertile offspring through self-replication. Not only that, but we will show how we can invoke self-replication with variation to generate novel images. And this will allow us to generate a genealogy out of training self-replicating sequences. And so at the end of this talk, it will be clear how we got to this. But to give you some pointers or like, some insight to understand where we are going to. In the end, we will generate some agents that are represented by the image that they encode, that are able to self-replicate perfectly if you ask them to, but they can also self-replicate with variation and generate novel flower-like images. So how do we get there? First, we will observe how the prior work on feed-forward neural network is incapable of generating fertile offspring. And the informal definition that I use for fertility is it's a recursive one. So I mean that they are capable of producing offspring that is both fertile, so this is the recursive part, and also it's not chaotic. And by chaotic, it will be clear with the images what I mean, but it's just not random. They actually generate something which makes sense. And then we will solve this problem by enhancing the architecture with the introduction of some fixed structures during self-replication, and also, importantly, by training for finding and generating a contraction or a sink in the parameter space of the self-replication function. And finally, we'll show how, if we know how to do this, then it will be trivial to generate agents that can self-replicate with variation. All right. So following the fashion of our of the prior work of Chang and Lipson and Gabor et al., we will use a feed-forward neural network. And the way that we will do it is we'll have two types of inputs that are accepted. One for the auxiliary task, in this case of the image encoding, and this will receive an XY coordinate that represents a specific pixel in an image. And if we ask them a specific coordinate, it will generate a specific RGB value. Likewise, we will have a unique identifier for each one of the positions of the weights in the neural network. This, for example, we will use a binary encoded weight, but any kind of one-to-one encoding would work. The quality may vary, but it wouldn't matter. And when we will ask them a specific, we will pass it a specific identifier, it will generate a specific float for the new value of the child for that weight. So this is for just one value, but what we will actually do is we will pass batches of inputs. So we will pass the entire XY coordinate grid for generating an image, and we will pass all the weight identifiers to generate the new child. So whenever we will show some pictures, they will be done as so. First, we will pass this input batch for the image to generate an image. Then we will pass a batch of identifiers to generate the new child, and then we will do the same for the child. Note that whenever we self-replicate, the architecture will be the same. The input batches will also be the same. The only thing that change will be the weights of the network. We will also train the models to be able to fit an auxiliary task, in this case by using an image encoding loss, which simply will be as follows. We ask the network to generate an image, and then we see how far away it is from the original image. All right, so the first task is let's try to fit this image. And we tried many things. We tried like everything that came to mind. We also tried to see what the related work was doing, and nothing is fertile. And by this, I mean that you could actually try to fit arbitrarily well for the original ancestor to be able to generate an image. As you can see, for example, in the sequence C, you can have a perfect quality on the original picture. However, the child will be infertile. And by this, I mean that when you generate the child, it could also arbitrarily be good and look like it's actually doing the same thing, but this child will be incapable of generating a child themselves. And this is actually looks like to be the general case for basically everything we tried, and also what is observed in Gabor et al. That is just not easy or feasible to find a child. We can also see that with a graph that shows the weight divergence of from the ancestor to their offspring. And you should interpret 10 to the minus 3 as being actually very close to the ancestor. And in fact, some of those images were actually capable of generating an offspring which looked very similar to the parent. And they were actually very close in weights. However, it was clearly infertile, and you can see that by the fact that the next child is random and is completely chaotic. So this is a problem. This is a very serious problem because, first of all, this is like when you use floating points, and also we train like this, we will generate inevitably an imperfect copy. First of all, because the self-replication function is not likely perfectly fitting the target, but also because you can't, because floating points can't have precise values. So if we use an architecture which has this behavior, we need to make it so even imperfect copies do not diverge, because otherwise we would not be able to accumulate any information across generations. I mean, if after every 2 generations you lose all the information, we will never generate arbitrary complexity because there's just no way of accumulating complexity. So we need to solve this. And the way that I explore in this work is by trying to find a sink or attractor or contraction. So I will explain what a sink is in the next slide, but keep in mind, this is one way to solve this problem. It's by no means the only one, but this is the one that we will explore here. So what I mean by sink is simply, we want to find a point in the parameter space of these architectures, which has the property that there exists a neighborhood where each neighbor, if we apply self-replication arbitrarily long, it will eventually converge to the sink, so to this parameter W, and stay there. So it will stay there forever. So this means that even if you would have an imperfect copy, it would still orbit around the original sink value and never escape them. And that would be exactly what we want. Now, can we train for that? And the answer is yes. So we can actually train it with what I call a sink loss, where we simply enhance the training regime by saying, whenever we want to generate a sink, we take the network parameters, we sample a random neighbor by just adding a Gaussian basically to each one of their weights, and then this new neighbor generates a child. Now, the values of this child will have to be as close as possible to the original neural network. That's it. It's very simple. And turns out that this is still insufficient. So if we try to find non-trivial sinks, we don't find them. And my supposition is that they actually don't exist. And this is consistent with what Gabor et al. Observed as well. Keep in mind that the reason why I believe that they likely don't exist is, in this case, it's even harder than just pure self-replication. Here we are saying you need to be able to perfectly self-replicate or like self-replicate nearby a sink. And also, this should be the parameter space that allows you to generate this kind of interesting images. So it is likely not going to be the case that when you can generate the image, it's also a sink. So can we do something about it? And the intuition for the second experiment is, well, we can actually morph the parameter space to generate those sinks. And we can do that by adding some fixed weights that will be replicated perfectly over generation. And I think the best way to interpret what we are doing here is actually, before we were having a fixed architecture and we were trying to find the parameters for this fixed architecture. Now we are meta training for finding also an architecture which is good for this. And the architecture will be generated by adding those fixed weights. And so now can we find an architecture that is able to self-replicate perfectly the remaining weights and also being able to fit for the auxiliary task. So from now on, every weight will actually be paired with a fixed weight or variable weight, and since it will be a proportion of them, a weight could be everywhere in between, being completely fixed and completely variable. Please note that if we just optimize for self-replication, then the training procedure would set all weights to be fixed, and we will find that trivial fixed point, which is completely useless. And by this I mean that we couldn't do anything more after that. So to avoid that, we add a loss that tries to minimize the amount of fixed weights to be used. So now the task becomes, can we find a fixed architecture that can generate perfect self-replication of a significant number of variable weights, and ideally the largest amount of variable weights possible, while also being able to perform a complex task. And again, this is a stepping stone. The final goal is to be able to generate some self-replicating agents that can also have some variation in the self-replication. But this, I will show that extending this will be trivial. All right, so finally we can make this work. So once we have both a sync loss and this new type of architecture, we are able to generate some agents that can self-replicate perfectly for arbitrarily long sequences. We tested it up to 300 self-replication routines, and we believe that there's sufficient evidence to believe that it will never escape it. I'll show it in the next slide. But first note that the resulting proportion of fixed weights to variable weights is that we found something with 28% fixed weights. This is the histogram. As you can see, some of them are completely fixed. Many of them are completely variable, and a lot of them are in between because this is a smooth procedure of training. So it was expected that that would be something in between. This is actually a non-trivial solution, and there's many ways that we can see that. If you're interested, please look at the code base where there's a lot of ablations and testing to show that that's the case. And we can go back to looking at the graph for weight divergence, and now we can see that, well, 10 to the minus 3 was already good to begin with, but over time, the distance between one another decreases up to insignificant values and stays there for at least the next 300 self-replication routines. So now we can try to extend this. Before, we only had a task of being able to self-replicate perfectly for this one image. And now we will have an ancestor that starts from here and tries to also being able to self-replicate with variation by targeting this or this other image, which are all effectively some channel swapped versions of this image. So how do we do that? It's very simple. We just add new inputs to the self-replication procedure. So now the self-replication procedure accepts the concept of input, which says, is it a self-replication with no variation? So ideally without making any change to your children, or is it one with a specific type of those three variations that I showed you before? And we also add sync losses for every target image. So we will effectively train for generating 4 syncs, one for each target image. And note also that the sequences that we observed during training are extremely few. The only thing that we train for are a sync loss with a no variation replication from the original ancestor, or performing one of those 3 operations, so right shift or left shift or channel swap self-replication, and then a sync loss with no variation replication. That's it. We don't do anything else. So this means that here, in this genealogy, only the things in blue are the things that we train for. So from this agent going into this agent and then performing a sync loss, from this agent to this agent and then performing a sync loss, from here to here and then performing a sync loss, or simply performing a sync loss here. Everything else is out of training. So the results, I think, are particularly interesting because of their variety of what we observe with such a simple training regime. First of all, we train for 4 syncs, so we would hope that at least there are 4 syncs. But actually, there are 3. So these 3 are able to self-replicate perfectly. So like if you ask them to self-replicate without variation perfectly, they will do. But the 4th one, actually, under close inspection, after 50 to 100 self-replication routines, it slowly converges back to this sync. And we observe this sync to be extremely powerful, as we will see in a second. Also note that if we instead keep performing a kind of self-replication with variation, something unexpected happens, and it's, well, the model did not learn to generalize to perform channel swap operation, actually, but it learned to go into a certain parameter space that it gets stuck to. So if you continue performing a certain type of self-replication with variation, it will generate a sync of its own, which we didn't train for, and is absolutely unwanted. This happens everywhere, like also for the other 2 types of self-replications. But very interestingly, and the thing that I found the most fascinating about all of this is, if we eventually start self-replicating without variation, the model goes into an exploration which actually generates variation, but it's a very interesting ones. They are all distinctly flowers. There are some of them, at least from my point of view, beautiful, and they generate different images that we never saw in training at all. So what happens if we continue performing self-replication without variation? Well, unfortunately, they will all eventually slowly converge back to this one sink, which was observed to be the strongest of them all. And we actually can prove that it's the same sink because it's in the same parameter location. But one thing that we would have loved to see was if this method would have also generated other sinks, which were completely out of training with this no replication type of variation. But this was not the case. And in fact, there are quite a lot of limitations that we need to address for future work. So, in conclusion, I would say that this work shows that it's possible to use deep learning for bootstrapping a model to be able to self-replicate with variation. And I hope it highlights the importance of optimizing for fertility of the offspring. I think this probably is the most important thing for any practitioner that wants to generate self-replicating agents. It would be my advice and call would be, please make sure that anything you do is fertile as the first thing you do, because it would hunt you back if you don't. You need to have agents which are fertile, otherwise you would lose all that you learned in the previous generations. And it shows that if you do want to generate self-replicating agents with this type of smooth architecture, you can actually do that, and you can still find stable attractors, for example. And ultimately, this is an encouragement for reviving this field, and not just with deep learning or differential optimization. I think that there will be very interesting approaches that can be tried with the pure genetic algorithms, for example, or even human design. I mean, anything that works. There are some limitations to address, quite a lot of them. The first is that it clearly generalizes poorly in some cases. I show you a few of them. It doesn't generate like many things. It gets stuck into some unwanted behaviors when you try to generate with variation. But deep learning shows that this should be tackled. It's possible to be tackled just by having bigger and more complex training regimes. This usually helps a lot with generalization. But more importantly, the space of possible outcomes is still limited. But by this, I mean we can never generate non-flowers with that. And we certainly cannot achieve general intelligence from this. This sounds trivial, but I mean, the goal is to generate extremely capable self-replicating agents that can complexify arbitrarily. And so far, some parts of the self-replication are still homo ex machina, so we actually put them there. And we can't have them, like the models cannot change it themselves. And ideally, we would want the models to be as responsible as possible for generating interesting variations on themselves. And well, if we want to have arbitrary complexification, we definitely need self-replicating procedures that can grow arbitrarily in complexity and can escape any kind of input-output type of values that they can accept. So, like, can they escape image generation? That is something that this model can't, but future work should definitely try to address. And with this, I open it up to questions. But before, please note that we have a code to reproduce this in a Google Colab, which is super easy to try, and you can find it on our GitHub. You can send me an email if you're interested, or tweet or follow me on Twitter. And thank you.